Good day, ladies and gentlemen. I am Maria Lorviana Canyon, 20, call me Vienna for short, taking Bachelor of Science in Civil Engineering, major in Structural. A third-year student at the University of Mindanao. I have a lot of hobbies that includes drawing and painting, although I'm not an artist. I also love dancing since I came from a family of dancers. I also play musical instruments and write poems from time to time. Now, if you're wondering why did I take engineering, and note that I am not good in mathematics. It's because I believe that you shouldn't run away from your weakness, but rather face it in order to overcome it. And I have other reasons as well. Moving on, how do you cope up in this pandemic? Coping in the midst of the pandemic is not simple. It's totally scary at first. Then eventually it became boring. You get to stay at your house for like 24 hours. And what you gonna do with much time? Stare at the walls? But then it hit me. I have a lot of things that I've been thinking of doing, but I couldn't because I'm busy. And now that I have much more time to spare, I get back to those things which are my hobbies. And I have mentioned it earlier. In addition, this situation is making me a couch potato. Because of this, I tend to eat and sit while binge watching some of my favorite animes, TV series, movies, especially from Hollywood. My hobbies are the main reason why my thoughts are still intact. You see, mental health is very important, especially in this situation. We gotta take care of ourselves. And for me, my hobbies are helping me cope up in this pandemic. Now, what's my favorite color? It's funny because when I was younger, my favorite color is pink because it resembles Barbie. And don't get me wrong, I do love Barbie. But when I grew older and go to the world, became more mature, it changed my perspective in life. And that life is not all about the material things. And now, my favorite color is blue. Why? Because it's the color of the ocean. Imagine yourself in a beach. Those warm breeze that kisses your skin, and those calm waves that you can hear. Soothing, isn't it? For me, that resembles peace and quiet, and I love that. And here's a kicker. I actually lived in a place where the Pacific Ocean is our backyard. So those warm breeze and calm waves feels nostalgic every time I go to other places. It doesn't just resemble peace and quiet, but it also reminds me of home, of where I came from. That is why my favorite color is blue. My expectation is the same to my other classmates. Perhaps all of us wants to learn about this subject. That's actually the very reason why we are here. Aside from that, I expect that in this class, I will learn not only the fundamentals of this subject, but to love the subject itself. Because for me, that's what true learning is. That's all, thank you. Now, moving on to the topic, precipitation data analysis, elimination of missing data, depth area duration, and frequency analysis. First part, we have depth area duration analysis. Generally, as the catchment area increases, the spatially average rainfall depth for the catchment falls. Data on the depth of rainfall for the storms is commonly presented as tables or graphs showing maximum average depth of storm rainfall over different areas and is called the depth area duration, DAD data. Thus, the DAD analysis is carried out to determine the maximum rainfall depth over areas of various sizes in different times. For example, maximum depth over 500 square kilometers in one day. Two methods are used to construct the DAD relationship. Number 1, the mass curve method, and number 2, the incremental societal method. In each of these methods, the time division of rainfall is treated differently. In the mass curve method, the mass curves of rainfall for individual stations are constructed. Then an average mass curve is prepared for the entire catchment. In the incremental isohyethal method, first, isohyethal maps are prepared for the maximum first day, second day, and etc. These maps are studied, and the map for the day that yielded the maximum depth over various areas is used to calculate the maximum one-day depth area. This step requires examination of maps prepared for various days. Next, the isohyethal maps for the maximum 2-day rainfall depths are prepared for various areas. Likewise, the DAD values for the maximum 3-day rainfall depths and etc. are obtained. The depth area duration relationship may be expressed mathematically as follows. P is equals to A times T over A plus BT to the power of M, where P is the rainfall depth in centimeter, T is the time duration in hours, A is the catchment area in squared kilometer, and A, B, and M are the parameters determined by regression analysis. Now let's have an example. Determine the one-day maximum rainfall depth for catchment areas of 250 and 5,000 squared kilometers located in United States. For the study area, we have A equals to 4.31 times 10 to the power of 3, B equals to 2.77 times 10 to the power of 2, and M equals to 0.803. Now we have our solution. Given time is equal to 1 day, which is equivalent to 24 hours, and catchment area equals to 250 and 5,000 kilometers squared. The maximum rainfall depth for A equals to 250 kilometers squared is computed as. Now we have our solution, which is the P equals to AT over A plus BT to the power of M. We just have to substitute the given to the formula. 4.31 times T to the power of 3, that is our A, times 24, and that is our time, over 250, our area, plus 277, which is the product of our B, that is equals to 2.77 times 10 to the power of 2, times T, 24 hours, to the power of 0.803. Now we have our P, 85.54 centimeters. Similarly, for A, that is equals to 5,000 squared kilometers, P can be computed as 56.17 centimeters. We just have to use the same formula for this one too. Now the storm center DAD analysis for one-day storm using the isohyethal method for a project is presented in table 21.2. where we have the depth area duration analysis computation for one-day storm during August 30, 1982. It may be seen from the isohyethal maps of various storm durations that 1. In general, the areal spread for a given duration decreases as the storm duration decreases, and 2. The average rainfall corresponding to the given storm duration over the area surrounding the storm center decreases as one moves farther from the storm center. The rainfall depth for a small area is reasonably represented by the rainfall depth recorded at a station, but the ratio of mean areal rainfall to the point rainfall decreases as the area increases. This ratio is much more sensitive for high-intensity, short-duration rainfalls. Hirschfeld and Wilson, 1960, reported the values of the ratio of average rainfall over the whole area to that over a 25 km squared, as shown in table 21.3. We have here the ratio of mean rainfall to that over 25 squared kilometers, as you have observed in here. Now the numerous depth area relationships have been developed. Leclerc and Shake presented a relation between the ratio of areal precipitation depth to point precipitation depth as this. where T is the duration in hours and A is the area in square miles. For the second part of our topic, which is the rainfall intensity duration frequency analysis. Rainfall frequency is the time elapsed on an average between two rainfall events of the same depth and duration. The actual time elapsed may vary by a wide margin. Events with larger rainfall depths are not very frequent, but events with smaller depths are frequent. The relationship between intensity, duration, and frequency for a given project catchment can be obtained by the analysis of short interval data. The data pertaining to the amount of rainfalls of different durations, such as 10 minutes, 20 minutes, 30 minutes, 60 minutes, 120 minutes, and so on, are processed to determine the rainfall depths for various frequencies. Plots of average rainfall intensity versus duration for a particular frequency give the intensity during curves. In many problems related to the design of water resources projects, it is required to know rainfall intensities for different durations and return periods. The relationship between rainfall intensity, duration, and return period can be expressed by the following general form. I equals to kt to the power of n over b plus t to the power of m, where k, b, m, and n are empirical coefficients for a given catchment that are estimated using measured data of the same catchment of region or experience. On 1969, Bell reported an empirical relationship between high-intensity, short-duration rainfall depth and return period as this, in which pt to the power of t is the depth of a t-minute, t-year return period rainfall, and p10 to the power of t is the depth of a t-minute, 10-year return period rainfall. He also expressed the ratio of pt to the power of t to pt to the power of 60 as a function n of t as this. As you can see here, this is the function n of t. Equations 21.5 and 21.6 can be combined to yield this. When records are insufficient for determining 60 minutes 10-year rainfall, the following relationships can be applied, where P2 raised to 60 is the 60-minute 2-year return period rainfall depth in millimeters. M is the mean maximum annual day rainfall in millimeters, and N is the mean annual number of thunderstorm days. For other durations and frequencies, the 60-minute 2-year rainfall can be employed to determine values as we have this. Let's have an example. Determine the 1 hour and 6 hour maximum rainfall depths and intensities for return periods of 2, 10, 20, 50, and 100 years for a project. The values of required coefficients are given as k is equals to 5.82, n is equals to 0.160, b is equals to 0.40, and m is equals to 0.75. Here we have our solution, where t is equals to 1 hour and 6 hours. The rainfall intensity for t equals to 1 hour and t equals 2 years is computed from equation 21.2 as this, where the corresponding maximum rainfall depth is 5.05 times 1 equals to 5.05 centimeters. IDF curves can be drawn in the same way as the depth duration frequency. Curves are drawn, but the difference is that the IDF curves use the data of maximum rainfall intensity and the DDF curves use the data of maximum rainfall depth. In figure 21.1 shows typical DDF curves. Note that the maximum rainfall depth increases as the duration and return periods increase. If the data of maximum rainfall depth and its duration is available, the maximum rainfall intensity can be determined by dividing the maximum rainfall depth by the corresponding duration to yield the data that is required to plot IDF curves. We have here in figure 21.1 the typical variations of the maximum rainfall depths of various durations with the return period. For this one, we have 3.06 rainfall duration and 4.1 rainfall depth. For the construction of IDF curves, the maximum rainfall intensities of various durations can be calculated from the data of maximum rainfall depth and corresponding duration. Frequency analysis is performed by using, for example, Weible's plotting position formula. An appropriate distribution, such as the log normal distribution, is fitted to these curves, where we have y is equals to a ln x plus b, where y is the maximum rainfall intensity, millimeter per hour, and x is the return period, in year. And a and b are the distribution parameters. As an example, the IDF curves at Baton Rouge Airport are plotted in figure 21.2. The figure shows that as the rainfall duration increases, the rainfall intensity decreases and vice versa. Further, the intensity increases with increase in return periods. We have here in figure 21.2 rainfall intensity duration frequency plots for Baton Rouge Airport. And that would be all for my report. I hope you learned a lot. Have a good day and God bless.